Hello. Today we are going to discuss about key management. This is the motivation for this topic. Without having correct keys, cryptographic algorithms are useless or even harmful. So we know that in when we use encryption schemes or some kind of message authentication using MACs, we have to share the correct encryption keys or the private keys used to uh, generate or the compute the MAC tags. So we have to share them uh, properly before using the that particular cryptographic algorithm. So otherwise, cryptographic algorithms are useful if these keys are compromised or may be harmful. Like if somebody can steal them, the cryptographic algorithm is harmful because we believe that due to the cryptographic algorithm, due to the encryption scheme or the message authentication code we use, we have the proper security, but actually the key is compromised and third parties can uh, gain the knowledge. We don't know that as well. So symmetric keys must be transported confidentially and authentically. Even public keys need to have their authenticity assured. So when we discuss about especially the symmetric key cryptography, the block ciphers or the stream ciphers or message authentication codes, we understand that the keys which are used to compute the encryption or the MAC tags should be properly, confidentially, and authentically distributed between the parties who are going to participate in the communication. And also, when we look at the public key cryptography, there we have mentioned about public key infrastructure, the PKI. So there should be a mechanism to provide authenticity for this public key infrastructure. So once I am given somebody's public key, there should be a mechanism that I have to believe this public key is from that particular person. So somebody should give some assurance about that. So that is done by public key infrastructure. That's a completely a well-established setup. So key management is subtle problem, and many protocols for key management have turned out to be flawed. So because of this criticality, like when we have encryption schemes or message authentication codes or signature schemes, encryption schemes can be public key encryption or symmetric key encryption. Anyway, there should be a way to provide the valid authenticity for the for distributing keys. So key management is a subtle problem because of that. If we like, if we have a very simple setup, or like there are not many users, we can distribute the keys somehow. We can meet the person and give the key in person, or we can use a trusted courier service, whatever, we can do that. But if it is a well connected networked setup and we even don't know the peers, that is very difficult to manage. So this key management is very complex and hard to solve problem. So there were many protocols proposed for this, but turned out to be flawed because of the complexity and difficulty of this key management problem. So when we have key management, so despite the availability of public key encryption and signatures, in practice symmetric key ciphers and MACs are used for long messages because they are greater efficiency. So we discussed that, like when we have the public key encryption schemes or signature schemes, we can do the encryption and do the communication without pre-sharing the keys, but still we have to have the proper public key infrastructure there. But again, even though we have that well-established public key infrastructure, having the public key mechanisms for encryption and signature schemes, it is like heavy in computing. So because of that, for long messages or the like streaming, data streaming or long messages, very frequent message transmission between parties, for that kind of purposes, if we use public key cryptography, that is going to be very inefficient. Because of that, we have to go back to the symmetric key encryption schemes despite the availability of uh, public key mechanisms in the world. So even though that symmetric key encryption schemes are efficient, the main problem there is how to manage, like how to distribute the secret keys. So we have public key mechanisms, but they are inefficient. Because of that, we have to use symmetric key encryption algorithms for our frequent message transmissions. So now we are at a point, like to get the great efficiency, we have to use the symmetric key stuff. And for that, we have to address that difficult problem of key management. So thus, we still need a way of establishing secret keys among the parties who are going to communicate. So usually we will want to derive a new session key for each communication session. So that means if I am going to communicate with my friend, then for this particular communication session, we have to derive a private key to encrypt our data. And again, if I am going to communicate with my friend in next week, we have to derive another new session key for that particular communication session. Otherwise, if we are going to use the key I have used today for next week, if somebody else could steal the key, the future communications will be revealed to the unnecessary parties. So that's why we have the concept of fresh session keys for each communication session. So the session key between two parties going to be different from session to session. Then we can guarantee that communication is well protected. Even though the session key is compromised, in future we can say, okay, now from this session onwards we have used fresh keys and they are not compromised. Because of that, we can guarantee the confidentiality of these sessions or whatever the security property we expect from there. So there are three main approaches for this kind of a key management. One is key pre-distribution, other is session key distribution, and other thing is key agreement. So these are two different approaches, two different meanings. Roughly saying, key pre-distribution means if there are two parties going to communicate, before the communication they are going to distribute the key between the parties. So if I'm going to communicate with my friend, what I'm going to do is I just go and meet him and pre-distribute the session key for our next session, communication session. Or through a trusted courier service, I can do the pre-distribution. Or otherwise, I can just make a phone call and do that. And then we use another communication channel for the data communication. So somehow we have to pre-distribute the key before the communication session starts. And other thing is session key distribution. So session key distribution is something like, for a particular session, there should be a way to distribute a key between two parties with aid of a trusted third party. That is particular for that session, we do the key distribution. In key, the first point, the key pre-distribution, it is like, even though I mentioned the term session, but not necessarily for a session, two people distribute a key for their future communications, regardless of sessions maybe. So in the second point, session key distribution, it is specifically somehow pre-distribute the key, but for that specific session. And session to session, the key is going to be changed. That means key should be pre-distributed prior to the start of that session. And key agreement is, it is not just distribute the key. It's like two parties provide some values and contribute to the key generation thing and agree on a value as a key. So in previous 2 points, key pre-distribution and session key distribution, it is not necessarily the two parties are going to agree on the value to be used as the key. It's like, if I'm going to communicate with my friend, what I'm going to say is, we will use this sequence of bits as the key, and I give that information to my friend, and my friend will accept that and use it. He's not going to contribute to create the key. But in the case of key agreement, I'm just going to contribute as do the partial contribution, and my friend will do some other partial contribution, and as a product of those two contributions, the session key will be generated. So that's key agreement. And then finally, both parties will agree on the key to be used. So both will contribute, and then both will agree on the key based on some computations. So these are the three mechanisms for how to establish an encryption key or message authentication code secret key prior to the data communication. These are the three ways we can do. As the first point, we are going to discuss about key pre-distribution. So in that case, a trusted authority generates and distributes keying materials to all users before users join the system. The pre-distribution phase is assumed to be done securely using some external method, manually, or maybe by going to the office of that trusted authority and get the keying materials, or using a trusted courier service, or personally meeting, or whatever, or phone call, or anyway, like some external method, not the communication, the wired communication we use for data communication. This should be some external method. And the availability of trusted authority is there. So that trusted authority generates and distributes the keying materials. Keying materials means in our the stream cipher sessions, we discussed about a seed value. Using a seed, we generate a key stream. So seed is a keying material, something like some value to generate the key. That's the keying material. And afterwards, users employing their keying materials to protect communication to each other. So that means using the keying material, they can, using another algorithm, they can generate a key stream or something like that. Then using that, they do the encryption process. The simplest scheme assigns a secret key for each pair of users, but then number of keys growing exponentially this is going to be difficult. Let's say, like, if I am the trusted authority for generate the keying materials, and I am facilitating the communication of two parties. For, for in that purpose, for these two parties, I generate a key material and provide to them. So this is simple when the number of communication parties are small. Let's say if there are many thousands parties communicating with each other, that means this managing this keying material is really high, because it grows exponentially. If there are only uh, two parties, there is only one keying material. If there are three parties, there are going to be uh, 1, 2, and 3 keying materials. So likewise, if it is uh, 4 parties, it's going to be like it is going exponentially growing the number of keying materials. So it is very difficult to manage this kind of process, the pre-distribution thing, even though we do not consider the uh, uh, communication sessions there. We just consider the keying material for just two parties, that is going to be fixed between two parties. If we consider the session keys, that means between two parties there may be many number of keying materials depending on the number of sessions. So it is going to be even complex. So there exists probabilistic scheme that significantly reduce the keying material at each party at the expense of only guaranteeing a secure channel between any two parties with some high probability. So as I mentioned, this key pre-distribution is going to be very expensive and hard to manage, hard to store, hard to distribute uh, if there are many number of parties for the communication. And the typical advantages of key pre-distribution schemes are: the trusted authority only operates in the pre-distribution phase and need not to be online afterwards. So that means I can be a trusted authority. I can be completely offline. I can open my office, and anybody can come to my office and say, "Okay, I'm Alice. I want to communicate with Bob. Give me a session key for that." So I give a session key, not a session key, just say a key for those two parties. So what I do is I generate a key and I give it to Alice and Bob. And from that point onwards, I don't need to be online. And no need for computationally expensive public algorithms. I can just randomly pick a value and then give it. And low communication overhead. The typical disadvantage of pre-distribution schemes are large amount of secure storage for keying materials, poor scalability. You can understand that. If there's only Alice and Bob, I can manage it. And Alice, Bob, and Carl, I can manage it. And if there are thousands, it is very difficult. Like, I have to store all the keying materials between each and every party. That's going to be a hard thing. And the next way is session key distribution. That's the second point we have discussed here. Session key distribution. The first is key pre-distribution between parties. So session key distribution is an online trusted authority generates and distributes keys to users when requested to do so. So that means not a value fixed for two parties. This is like key for two parties upon a request for a communication session. The distributed keys are used for a short period called sessions, and a trusted authority shares a long-term shared key with each user, which is employed to distribute session keys. So in this way, in the previous case, the key pre-distribution phase, the problem is when there are a lot of parties, number of parties, the number of communication between parties, that means number of connections going to be exponentially high, and that means need of having distinct session keys is a problem. That means if I am trusted authority, it is not suitable to give a same value as the key for Alice and Bob and something like Rama and Sita. So that means there may be a conflict, and if somebody who has a set of session keys who can compromise a set of session keys can try that set of keys for other parties. So if I have the key of Alice and Bob, I can try that key for Rama and Sita, Carl and Dave. Likewise, I try that, and at some point I can find a collision. That means same key is used between other two parties. So that problem comes when we have the key pre-distribution there. But in this case, in the session key distribution, the key is delivered to the parties for a session, for a short time only, and from that session now afterwards, that key we can reuse that key for any other session, so that communication is not going to be fixed, that key is not going to be fixed between those two parties. So an online trusted authority generates and distributes the keys to users when requested to do so. The distributed keys are used for a short period, and the trusted authority shares a long-term shared key with each user. So if I am the trusted authority, I use a long-term key between myself and Alice, myself and Bob, myself and Carl, myself and Dave. Likewise, I have to have long-term keys between myself and each of the party, and using that key, I generate a session key and encrypt that session key using the private or the long-term key I share with other party and give that key to the other parties. So the advantage of session key distribution schemes are no need for computationally expensive public key algorithms. The trusted authority can just randomly pick a value and give it for a session between two parties, and only a small amount of secure storage is required by each user to store the long-term key. No certificate management overhead, and also the typical disadvantages of this scheme is it requires that trusted authority to be available online, and TA is highly trusted and is a single point of attack. The security of the whole network depends on that trusted authority. So because he is going to be available online all the time. In the previous case, trusted authority need not to be online. He can be offline. So attacking is kind of difficult. But here, trusted authority is available online all the time, and it's a single point of attack. And here, no certificate management overhead, no need that. And also, only a small amount of secure storage is required by each user to store the long-term key. So every user has to share the long-term key, store the long-term key between uh, himself and the trusted authority, and trusted authority will store everything, long-term keys between himself and uh, the, the the users, and randomly picks a session key and give it. In the previous case, every party should keep all the secret keys that they are going to use between other parties. So very difficult or very heavy storage should be there. But in this case, only one key should be stored by the users, and session keys, the person that the trusted authority can randomly pick and give it, and after the session it will be discarded. But since the trusted authority is going to be available online, it is going to be the single point of attack. And this is one of the uh, famous session key distribution protocol, Needham-Schroeder. So this is proposed in somewhere like 1978 or something. And by that time, this public key infrastructure and this public key cryptography and the TLS SSL protocols we use currently are not established. So this protocol is proposed as a method for establish the session keys, the session key distribution protocol. So in this protocol, you can see the notations. Parties are A, B, and S. A, B are the two parties who want to establish a shared key, and S is the trusted authority. And shared secret keys, KAS, is the key shared between A and S, A and the trusted authority. KBS is the key between B and the trusted authority, and KAB is going to be the session key, fresh session key given by the trusted authority for to be used between A and B. And this is how the protocol works. First, so these are the nonce. Nonce means a number or randomly generate value for one-time use. And the second point, the nonces are in A and in B. And the second point, S to A, means A sends a message M to A. And the third point says value in A, comma A and B, KAS, means encryption of authentication nonce in A and identities A and B using the shared key between A and the uh, trusted authority, which is KAS. Okay. Now let's look at the diagram, protocol diagram of this protocol. Here we can say the story is like this. A needs to get a session key to communicate with B. So what A does is, A sends a message to the trusted authority S. That is the first message saying, I am A and I'm going to communicate with B, and this is the nonce. Nonce is a randomly generated value, and send it to S. That is used for to indicate that this session is this request is a fresh request. So A is his own identity, and B is the identity of the party he's going to communicate with, and NA is a nonce, randomly generated value, to indicate that this is a fresh request. Once S get this, what S does is, S randomly picks a value KAB. KAB is going to be the value, the key value between A and B. S picks that, and say the identity of A, the party who requests, and the identity of B, that is the party that A is going to communicate with, and NA, the nonce value sent by A, and also the KAB, that is the session key, fresh one, and identity of A and identity of B encrypted. These three values inside these small these curly brackets are encrypted with the secret key shared between S and the B. B is the party that A is going to communicate with, and the whole value is encrypted using the KAS value, that is the secret key between S and A. Once A get this, A can decrypt the value because A and S knows the KAS value, and now A knows that this is the session key and these are the two parties. uh, that means his own identity and the identity of the party he's going to communicate with, and he knows NA value. NA means the value he freshly generated and sends to S. Now he knows this session key is for this request because he knows this is the value he freshly generates this NA value, and once the session key comes with that value, he knows that okay, this session key is generated by S particular for the request sends at this point. To that is like uh, that guarantees that this KAS is generated for the fresh request of A with the nonce NA. And once he get that, he knows the value KAB, and he can't do anything with this the second part of this message, that is KAB, A and B encrypted with KBS. He can't do anything because he doesn't know the KBS value. He just sends it to B. This is the value I get from the trusted authority, encrypted using the shared key between you and the trusted authority, and this is my identity, the A. You may decrypt the message from the trusted authority and choose the and get the session key. And once B gets that message from A, B knows that this message came from A, and B can decrypt this entire message because B knows the secret key between B and the trusted authority, that means KBS, and now B get the value KAB, and since inside that message it indicates the identity of A, now B get to know that okay, actually I'm going to communicate with A because that is guaranteed by the trusted authority in this encrypted message. Now what B does is B randomly picks a nonce and encrypt that nonce using KAB, the fresh session key. Once B get it, what B does is B decrypt it using the KAB value and then -1, like reduce 1 and encrypt that value using KAB and send to B. Now when B get that message, B can see that okay, this message, when I decrypt the message, the value is going to be the 1 minus of the nonce I generated, that is NB. Like that, all the parties agree and satisfy with the freshness and authentication and everything. Then A and B will be in a status that they can properly trust there is a fresh session key for this communication session. So this is the Needham-Schroeder protocol. And this protocol is most widely known key establishment protocol and published in 1978. It has been the basis for many related protocols, including well-known Kerberos protocol. We have discussed about Kerberos protocol. Uh, no, I didn't put that in my YouTube channel, but Kerberos protocol, for your knowledge, Kerberos protocol is a protocol to provide authentication between parties. You can search in internet and get some knowledge about Kerberos protocol. It is an application of symmetric key cryptographic algorithms. So it is mainly this Needham-Schroeder protocol is a basis for a lot of well-known protocols such as Kerberos and many others. Unfortunately, it is vulnerable to an attack due to Denning and Sacco in 1981. They published a paper and they revealed an attack for this nice protocol. So attack on Needham-Schroeder protocol is when considering the security of key establishment protocols, we typically assume a strong adversary that knows the details of the cryptographic algorithm involved and is able to eavesdrop all the messages sent in a protocol. Eavesdrop. Eavesdrop means he can look at the communication and see all the messages transferring in the channel. So in cryptography, we assume that there is an adversary who can do the following things. Strong adversary who can do the following things. These are the things listed. Eavesdrop all the messages. That means he can see all the messages, all the encrypted messages he can see, but he cannot decrypt anything. But once a message is transferred, he can see there is a message and he can look at the ciphertext. So that means like anything like our communication channel or the internet service provider can see anything transferred. Even though it is encrypted, he cannot, once it is encrypted, he cannot see the actual values, but anyway, he can see the ciphertext. So that kind of person is indicated in this adversary. An adversary who can eavesdrop all the messages. Another thing is alter all the messages sent in a protocol using information available to him. So if I send a message to my friend, this strong adversary can replace any other message. He can see, as the first point, he can see the message, not the message like the encrypted message, he can see the ciphertext. And if he wants, he can steal that part and he can put any other thing. And my friend will get that and he will use it. If he can decrypt it, perhaps he will mislead that this message is sent by myself. Or maybe attacker can send even instead of myself, he can say, okay, someone else send this message. That kind of alterations can be done by this strong adversary. And reroute any message to other user. Like if I send a message to my friend, this kind of adversary can send that message not to my friend but to somebody else. For example, if I send a message to my girlfriend, this kind of adversary can send this message to my wife. That kind of adversary. And obtain the value of the session key KAS used in any previous run of protocol. So any previous runs of protocols, like if I'm going to communicate with my friend for this session, okay, this session, this adversary doesn't know the session key, but that adversary can get the values we use for previous sessions. He has that sort of knowledge. So in cryptography, we assume there is an attacker who has this kind of capabilities. So we are going to uh, design protocols thinking that there is such a strong adversary. We have to make our protocols uh, that is safe against this kind of a strong attacker. So that's the level we are trying to achieve. Like we say, this adversary is very strong. So for example, uh, if all the points I mentioned here are going to be matched with your internet service provider. Let's say like your internet service provider is an adversary. He has this kind of power. So we are going to create protocols in a way that even our internet service provider or such strong adversary cannot be able to decrypt the messages or alter the messages. So if he alter something, there should be a mechanism inside the parties to detect that. So this is the level of attacker we assume. And if we assume such an attacker is available, then an attacker C finds out an old session key KAS prime previously established between A and B. In the attack, C masquerades, that means hides or replaces, as A, and thus able to persuade B to use old key KAS prime. So instead of this fresh session key KAS, such a powerful adversary who has the knowledge of KAS prime, a previous session key between A and B, can persuade or force the users to use the persuade B to use that KAS prime instead of the fresh session key KAS. So how it happens is the protocol runs the point 1 and point 2 same as this one, and when it comes to the third communication point, instead of this KAS, AB encrypted by KBS and identity of A, instead of this third message, this attacker replaces it with KAB prime A and KB, which is encrypted with KBS. So this session key is previously used by A and B, and because of that, attacker knows there is a message, the third message transferred between A and B. Attacker knows that, and what attacker does is replace this third message, the proper third message, with this fake third message. And now once B get it, B can decrypt the value using the session key, the shared key between trusted authority and B. Once B decrypt it, B get KAB prime is going to be the session key between A and B. And B chooses a random nonce and encrypt it with KAB and send it to A. So now what C or this attacker does is, attacker can decrypt this fourth message because he knows the KAB prime value, and compute the NB minus 1 and encrypt it using KAB prime and send it to B. Now what happens is B trusts that I'm going to communicate with A using a session key KAB prime. But A is expecting to communicate with KAB, but C comes in between A and B and do this alteration. Now B will encrypt secret messages and send to A. A won't get it. Once the message is in the transmission, C will get it and do the decryption because C knows KAB prime and get the value. So this is kind of an attack on the Needham-Schroeder protocol. So because of that, there was another fix came to this thing, including another freshness. You can read this slide and understand how this attack mitigates introducing another freshness. So define against this is called replay attack. Replay, like get values from previous transmissions and replay with them. And this is repair Needham-Schroeder protocol to mitigate that attack. And I will upload the slide. You can see how it works. And so that is how the key session key distribution worked. So that is the third point we discussed. Pre-distribution, it is problematic, it is difficult because of the storage and everything, and session key distribution is okay. There were two problems, like because the trusted authority is the single point of attack there, and trusted authority has to be online always, and also we talked the famous session key distribution protocol and possible attack on it, and repaired Needham-Schroeder protocol, and again another attack proposed for this. If you read literature, you can find it, and another technique came to mitigate it. Likewise, there was a conflict between the attacker and the developer going on. There was, and the third point is the key agreement. So in previous case, two parties are not going to contribute or give the values to generate the keys. They rely on the value coming from the trusted authority, the third party. But in the third point, the key agreement, network users employ an interactive protocol to construct a session key. So two parties are going to construct a session key for that communication session, not the trusted authority. No online trusted authority is usually required. So the trusted authority not necessarily to be online always, but public infrastructure should be there. The key agreement protocol usually employ public keys for authentication, but can also use long-term secret keys shared between users. But in today's world, we use key agreement based on Diffie-Hellman protocol. This is a key agreement protocol. This is the basis for key agreement protocols nowadays, and for that we use in our day-to-day communication we use public key infrastructure, public key for authentication, not the long-term keys shared between parties, because we don't know the parties now. All the parties are connected to the internet, nobody knows each other, and because of that we trust on a public key infrastructure. An example of key agreement protocol is authenticated Diffie-Hellman. So this is not just the textbook Diffie-Hellman or the simple one. It's authenticated Diffie-Hellman. We looked it at in the previous lecture. You can find it in the YouTube and also in the lecture notes. So this is the idea of key agreement. If you look at the Diffie-Hellman protocol, you can understand there is no trusted authority providing the values for the communication, the session key generation, but only the parties Alice and Bob, or A and B, is providing simple A and simple B values and do the communication and share the values and then generate the session key as a product of G to the power AB. So nowadays in world, we do not use key pre-distribution or SKD or the session key distribution protocols. Instead, key agreement came into the picture because we can easily use them uh, using the public key infrastructure and also two parties contribute for the key generation, and because of that there's a strong trust between the parties about the freshness of the key. So this is a comparison between key distribution and key agreement. So when we talk about key distribution, it is key pre-distribution or session key distribution. The only difference is in pre-distribution it is fixed for two parties. In session key distribution it is fixed for two parties just for one session. Anyway, uh, the the difference between between key distribution and key agreement is the advantages are typical advantages of key agreement protocols are no need for a trusted authority to be online. In session key distribution, we have to have the trusted authority online always. That is actually the point, the one of the most vulnerabilities of that way. The users agree on a key by themselves and no need to trusted third party to contribute to that key generation. But trusted third party is there to establish this public key infrastructure for that certificate management part. Use of public key signatures allows non-repudiation. And typical disadvantages of key agreement protocols are if public keys are used, there may be high certificate management overhead. That means public key infrastructure should be there. But this is not problematic nowadays because public key infrastructure is well established. Because of that, we can say we can manage it. But if we are using this as a uh, like as a fresh construction, then this is a problematic or difficult task. Users are trusted to generate good session keys, so a good pseudo-random number generator is required at